If you've ever tried to use multiple coding agents in parallel, you already know the problem. You get speed, and then you pay the price at the end with merge conflicts and inconsistent changes. So in this video, I'll be showing you a workflow that scales cleanly. We're going to be using tmux to run multiple Claude Code agents side by side, and Git worktrees, so each agent works in its own isolated checkout. To put all this together, we have a simple review plus merge lane, so you stay in control. By the end, you'll be able to take a task list of 5 to 10 items and run multiple agents concurrently without turning your repo into a mess. So the mental model you want to have for this task is a mini agent swarm that's still Git native. So you still have a clean main or development branch, but you have each task becoming a worktree, which is a separate folder, a separate branch with the same Git store. Each worktree gets a dedicated tmux pane in this workflow, which runs its own agent, and you maintain one control pane for deciding tasks, setting constraints, reviewing diffs, and merging in a controlled order. Worktrees are the key here. They eliminate the biggest source of chaos, which is agents stepping on each other's files. So looking into the setups, something which you would expect to see after a planning stage to implement a new feature in Claude Code, for instance, is a document like this tasks.md, where we essentially have a list of tasks which the agent has created in order to implement a specific feature. You can also think of this as a list of issues in your repository. At the moment, if you go about implementing each one of these tasks in order, you'll be working in serial, and it's going to take a significant amount of time to get through all 5 of these tasks. If in theory these 5 tasks are quite separated and handle a different subset of files, then you're essentially leaving a huge amount of compute on the table where you could be running multiple coding agents, tackling each one of these tasks in parallel, essentially making it 5 times as fast. So for this example, I'm going to be using a mock repository with 5 tasks, which I've already set up. So you can see those tasks here. The first one is fixing some failing unit tests for this trading bot. Another one is implementing a CLI flag. One is to optimize hot loops in a specific Python module. And another one is improve logging. And finally, to update docs. So what's important here is that the agents don't have vastly overlapping tasks. So parallelism works when the file level overlap is minimal. So what we're going to be doing here first is we have the directory here, and we're going to start off by creating what we call a Git worktree. So a Git worktree is essentially a copy of your current branch which you're working on, and you can do this by using the following commands. So first we're going to create a directory where we want to store our worktrees, and then we're going to create one branch plus worktree per task. So we go git worktree add, so there we have it. So a quick note, we essentially use the syntax git worktree add path, then -b branch, which creates a new branch and checks it out into a separate directory. All the worktrees have the same Git object database, so it's fast and disk light. Now we're going to go ahead and create 5 worktrees for each one of our tasks, and we'll get back to it. So now we've gone ahead and completed implementing 5 work trees for each one of the tasks. And what we're going to do now is open a tmux instance so we can run multiple parallel agents. So in order to do that, I'm just going to call tmux here, and you can see here that we've got a new tmux instance with the name swarm. It's pretty straightforward to get tmux installed on your system. I'll be linking some links down below on how you can do that. It's essentially a terminal multiplexer which allows you to handle multiple terminal instances in a single window. So now that we've got tmux open, what we're going to be doing is going ahead and opening multiple panes. So we're going to have one control pane and 5 different panes for 5 agents working in parallel. So I'll go ahead and do that. So perfect, now we have our tmux instance with 6 panes. What I'm going to do now is go and use the top left pane for my control and the remaining 5 panes for individual agents. So I'll go and cd into the required work trees. So this one is for the first task. You can see we have our git branch here, which we've done from our original branch. And great, now we're in the individual tasks for each one of these panes. What we're going to do now is go ahead and open a Claude instance in each of these branches. So we'll do that in the same order. Great, so now we've got 5 Claudes running in parallel. So to recap, in each pane I start a Claude code, I give it a single task, an explicit definition of what it means to be done, explicit constraints, and a stop condition like open a PR ready commit and summarize the changes. So I'm going to be doing an example with the first prompt, so we're going to be typing something like, if we just go on to our first task, fix failing unit tests in pricing module, don't change public API, make the tests pass and add regression coverage if needed, run tests locally, end with a short summary and a list of touched files. So with this, we can go ahead and set this Claude off to run on this task. And that's going to be working independently. And once it's done, it's going to come back to us and ask any questions in the meantime if it needs to. In the same way, we're going to be doing the same for all the remaining agents, and I'm going to be giving a similar prompt for each one of these, so I'll copy them over. And now we have all 5 agents running in parallel, and we're going to be getting questions from each one of them. So we just go through and respond to not keep them stalling for too long. So just because this is an example, I will be giving all the access that Claude needs for these tasks. And now we just wait to see if it needs anything else from us and let it do its thing. Great, so now we have all of the agents completed, and let's go ahead and look at the changes which these agents have proposed. So this is for task 1. We have a summary. It had two failing unit tests in the pricing model, which it goes ahead and claims to have fixed. We have a summary of what these fixes are and the files which it's touched. So this is in our first worktree. If we go ahead and look at task number 2, what we get is successfully implemented task 2, which is to add a CLI flag for dry run. So it explains to us what it's done here and said that there's 8 CLI tests which are added, and 2 of them are failing from a pre-existing bug, but this was the task of task 1, so it doesn't go ahead and touch that. So we have a certain level of independent changes going on there between the agents. Similarly, if we look at the agent working on task 3, it was working on optimizing a hot loop in the order book with the following changes which are implemented. So it gives us a list of changes. It shows that all of the tests still pass in the order book PyTest framework, and yep, again, 2 tests are failing is from a different task, so no overlap there. Finally, if we look at the last 2, we have the improving logging around retry logic. So it implements rate limiting, timeout errors, connection errors, and unrecoverable errors logging for all of these. Added 10 new tests, and all of these tests pass. 2 failing tests from task 1, which it does not touch, and the documentation task at the end here, we can see it's completed task 5, and it shows us the file which it has touched. So what we see here is that these agents were able to work quite independently, and they didn't overlap on the files which they touched. So we shouldn't have any merge issues here, but in theory, if there was overlapping files, then we'd be able to merge these work trees using how we would traditionally merge conflicting changes. So if we go back to our master view here, and what we're going to do now is merge each one of these changes. So this is where we end up having some issues if we just merge in a random order. Of course, we want to merge the low risk and the low overlap branches first, which would be the docs and the logging, then merge the feature branches, and finally merge refactors and performance improvements last, since they tend to touch the most number of files. So in the main repository, what we're going to do is we're going to check out domain, git pull, and then sequentially merge each one of the tasks which we've implemented. First, we're going to be merging the docs, and then we're going to go ahead and merge the logging, next the dry run CLI, then the test, and finally the performance. So thankfully we didn't have any conflicts which happened in this, but if you did have isolated conflicts, then you can deal with them one by one, how you traditionally deal with merge conflicts. And there we have it. So what we've managed to do here is merge all 5 of these changes. So starting off, we had a plan which had 5 subtasks. We were able to isolate different parts of these subtasks and delegate them to a single agent. We ran 5 agents in parallel, and made sure that each one of the agents were able to focus only on the task which it was given, run tests, write tests, and make sure everything is clean on the given work tree which it was working in. And once we were happy with the results from that, we go back into our control pane where we have access to all of these work trees, individually merge each one of these work trees until we have a clean final repository which we can push upstream. So instead of sequentially running one agent on 5 tasks, we were able to parallelize it and coordinate each of these into completing the problem we have. What's interesting is that none of this is required new tooling. We're stretching infrastructure that was built for humans to support agent-first workflows. And that should already tell you something about where things are headed. Right now, we're still doing coordination manually, like assigning tasks, reviewing diffs, and resolving conflicts. But it's not hard to imagine the next step where agents negotiate ownership of files, resolve conflicts before they happen, and converge towards a single coherent change. Git wasn't really built for that, but workflows like this are how we can get around it. If you found this useful, then feel free to subscribe. I'm going to keep going deeper into agentic coding workflows for real systems, scientific computing and infrastructure problems, and what it actually takes to integrate AI into serious engineering work. So if you're already experimenting with multi-agent setups, then please leave a comment below breaking down how you use it and what you wish your tooling could do in the future, and I'll read through them and respond to you. Thank you.